My name is John Heisman, and I work for NGS Software, based out of London. I've given a couple of talks before at Black Hat. This is my first talk at Vegas. If you've seen any of my other work, to quote The Simpsons, you may remember me from such talks as implementing and detecting ACPI BIOS rootkit, and its much anticipated sequel, implementing and detecting a PCI rootkit. Today I'm going to talk about the extensible firmware interface. I certainly know that some of you in the audience are very familiar with EFI. Others, I guess, will, from using a MacBook, for example, will have a passing knowledge of it. And I suspect some of you may have heard of it but aren't exactly sure what it is, or at least some of the details of how it's implemented. So this is what I want to cover today. Actually, I'm going to start this talk by talking about the legacy BIOS, the traditional BIOS. So we're going to talk about the function of the BIOS on non-EFI systems, older systems. We're going to talk about means of attacking traditional BIOSes, since many of these are applicable to EFI. We're going to talk about the limitations of the legacy BIOS just briefly, because this provides us with some motivation for why Intel started to develop a replacement. I'm then going to briefly introduce the EFI environment. We'll cover the major components. We'll then move on to means of attacking the EFI environment, and we'll make reference to the attacks that we talked about for the legacy BIOS. I then want to talk about the successor to EFI, UEFI, and what the future holds. And we'll draw some conclusions off that. Firstly, some caveats about this talk. Most of my talks regarding rootkits have not been about what the rootkit actually does. I'm more concerned about means of persisting a rootkit, or even just some malware. And I'm concerned about persisting it in such a way that we can subvert the operating system as it's loading. So I'm not going to talk about the actual specifics of the rootkit that I refer to. In general, the rootkit I refer to is simply a rootkit that subverts the kernel in some way. So it may manipulate kernel data structures, it may simply patch functions in the kernel to provide a backdoor. Second caveat is that this talk isn't about trusted computing, though I will make mention to it. The EFI spec certainly doesn't mandate that you have to have a TPM, for example, in your system. And when I started looking at EFI on a MacBook, my MacBook doesn't have a TPM. So whilst, as I said, I'll make reference to it, it's not critically important. Some of these attacks will require physical access. When we talk about flashing firmware, for example, some devices, depending on the device, require flipping a jumper. Almost all of these attacks, I'm not going to talk too heavily about how we actually carry out the attack from its initial concrete implementation. Simply the ability to flash firmware. Most vendors have a number of tools available to do this. Reverse engineering those tools or just downloading chipset specs will give you that information. Most of these attacks could be implemented as a blended attack. So, for example, we chain a bug in a browser. So, user visits a malicious website that owns the browser. If they're running as admin, that's great. We can typically load a driver on most systems. Obviously, 64-bit Vista we can't, unless it's signed. So we may need, if we're not running as admin, we may need some sort of escalation to admin, or ideally an escalation from user mode to kernel mode. And then we can target the firmware. And I'd also like to say that parts of this research are definitely still work in progress. EFI is a complex beast, and UEFI is also very interesting. And I apologize that there's no white paper in the Black Hat handouts. If you'd like to check the NGS software website in about a month's time, then I'll have a white paper up there that covers all of this and actually goes into some more detail on some of the attacks. So let's briefly go over the role of the BIOS. When you turn your system on, the CPU starts executing from a fixed address, a reset vector, and ultimately it doesn't know anything about your hardware. First thing it must do, the firmware must do, is initialize the memory controller, the north bridge, and the south bridge, so that we can actually start talking to devices on the bus, on PCI bus, for example. The second thing it will typically do is, as we get going, it will locate option ROMs. So PCI devices on the bus typically have an expansion ROM, a ROM that is scanned for by the BIOS, copied into physical memory, and then executed from physical memory. So, for example, your video card has an expansion ROM or an option ROM. I'll use those terms interchangeably. The BIOS also provides some means of user configuration. So, for example, the familiar setup screen where we can configure hardware, and we can also configure the boot device priority, so we can choose a hard disk to boot off. And we can also persist those settings to some non-volatile RAM. And finally, the BIOS will launch the bootloader. Actually, that's not strictly true. It will simply launch whatever's hooked into 19. But in most circumstances, we'll want to load the bootloader, which will then load the operating system. Some means of attacking a legacy BIOS. We can simply modify the BIOS code itself and then reflash the firmware. The way this attack would work is that we'd obtain a BIOS typically from a vendor website. This is after we've done our due diligence on the system that we've attacked. So typically we'll have compromised the system, we'll have determined what hardware it is, what chipset, motherboard, etc. We will then visit vendor's website, get a reference, get an implementation of the BIOS, download that BIOS. Typically, the BIOS will be compressed data. When we decompress it, we'll find that it's a collection of code modules and data modules. We can start disassembling some of the code modules, patch them, compress it back up, and just use standard flashing tools or our reverse engineered equivalent of those tools to flash it back. Second option is that we can modify PCI option ROMs, so we can actually flash the firmware on PCI devices. And as I briefly mentioned on the last slide, during a power-on self-test, the BIOS will actually copy those option ROMs into RAM and execute them, so our code gets executed in the BIOS. Third option is we can modify the advanced configuration and power interface tables. These will basically be one of the data modules in the BIOS, and I'll talk more about ACPI attacks later. And fourthly, we can carry out some non-persistent warm reboot attacks. So by non-persistent, I mean essentially when we power off the system, we essentially lose our rootkit. But as long as we keep warm rebooting the system, we stay in memory. How might we go about patching the BIOS? Well, to be honest, there's a ton of places we can insert code. But ultimately, our goal is to subvert the bootloader. Bootloader is responsible for loading the kernel. So if we have code executing inside the bootloader, then it's a short step to patch the kernel. In a legacy BIOS, the bootloader must rely on a set of services exposed by the BIOS. And this is through the interrupt vector table. So this is the x86 real mode interrupts model. And basically, the IVT is built up dynamically. So, for example, things like a video card will basically register that it's the handler for int10 hex video. As I've already mentioned, the BIOS will call the bootstrap loader vector, which is int19 hex. So, just when it's leaving, when it's about to launch the bootloader. So ultimately, an attack here is that we just need to find where it passes off control, where it calls int19, and we need some code before that modifies the IVT, and we basically hook an interrupt. On my next slide, or in a couple of slides' time, I'll talk about what interrupt we might choose, but it's a fairly simple process. Some caveats: as I said, it may require physical access. And also, this attack assumes that we don't require signed updates for firmware. I'll elaborate a bit on PCI option ROMs. So the ROMs on PCI devices hold initialization code, and most likely this code is x86 code. And during the post, it's simply copied to RAM and executed. And typically it's stored in an EEPROM or an EEPROM, the difference being whether we need to actually remove the chip to flash it or whether we can do it while it's on the card itself. An example here is if you buy a PCI Express graphics card, then typically you'll have an EEPROM on it. And if you dump the ROM off that card, you'll find that it will hook int10, and this is to implement VGA and VBE BIOS functions. And actually, a clarification when I talk about PCI, ultimately I'm using that term to mean PCI, AGP, and PCI Express, because the option ROM mechanism is the same. How we'd attack an option ROM. Obtain the option ROM. This is pretty easy. We can either go to the vendor's website and download latest version, or we can just rip the ROM directly off the card. If you look at the PCI spec, it talks about how to actually program the card so that you can dump the ROM into physical memory, so we contain an exact image of it. Flashing is pretty easy. We simply need to do I/O to the card. Again, the way I would do this is start by finding the vendor's tool to actually do this and reverse engineer it. Patching the option ROM, again, we're going to target the IVT, and we want to hook an interrupt, and when the bootloader calls that interrupt, we then have the ability to patch the kernel or kernel modules. So to answer the question of which interrupt to hook, well, EI produced a boot sector rootkit, and they took the route of hooking int13 hex, as in disk. So basically, every time int13 was called to load a kernel module, or the kernel itself, then essentially they would filter the data coming back and look for a particular byte stream and just patch it on the fly. When I talked at Black Hat DC about PCI rootkits, I chose int10 hex video as my target interrupt, and this was a Windows-specific technique because I noticed that the Windows kernel actually calls int10 fairly late in the boot, and the reason it does this is it switches into V8086 mode, because obviously the Windows kernel runs in 32-bit protected mode, and so essentially in order to call int10 in the real mode interrupt vector table, it's necessary to switch into virtual 8086 mode. So switch the processor into that mode and then execute my code, execute the int10. And because I've hooked that int10, I can detect this case. And ultimately, I was able to influence the context structure that the operating system used to return from V8086 mode. Ultimately, there are likely to be other candidate interrupts that you can hook. The legacy BIOS, as I said, the bootloader relies on services exposed by the legacy BIOS, so ultimately it's at our mercy. Pros and cons of option ROM attacks. One of the benefits is you typically don't have any write protection on the cards. As I said, flashing is pretty easy. We just need to do a few I/O instructions to the card. Almost all things like graphics cards these days, standalone graphics cards, can be reflashed. Network cards also typically come with option ROMs these days that implement PXE, and PXE is quite nice. PXE is the network booting, essentially, and so ultimately we've got a networking stack already on the option ROM. When I talked about PCI rootkits, I mentioned the possibility of using the PXE code to actually perform pre-boot updates of our rootkit. One of the cons of this approach is that we're typically limited in space to only a few kilobytes. You could get around this by perhaps distributing your rootkit across multiple PCI devices, but we're talking a fairly specific solution here. Unfortunately, detection of this kind of rootkit is fairly easy. It's quite easy to dump the ROM from the card and then perform some static analysis and have a set of heuristics. Giveaways, for example, if we have any protected mode code in the option ROM, this is typically pretty suspicious. The detection process could be subverted in a few ways, though. We can apply standard standard malware code obfuscation techniques to the ROM, and also, as I'll talk about later, we can even prevent the operating system from dumping the ROM. The next attack I want to talk about for legacy BIOS implementations is ACPI. This is a slightly different attack to the previous two, in that ultimately we're not interested in subverting the bootloader at this point. We're interested in subverting the Windows kernel or the operating system kernel itself. This is abstraction of ACPI implementation for an operating system. Ultimately, you can see that the core of it is the ACPI driver in the middle, and this is a operating system device driver. So those of you not familiar with ACPI, it's the Advanced Configuration and Power Interface, and ultimately it handles all the power management on modern systems, whether they be servers or notebooks. And with Apple's switch to Intel, they had to basically start using ACPI. The way ACPI works is that the BIOS, which is represented by the dotted line, contains some tables, the ACPI tables, and these tables contain instructions for an interpreter which is implemented in the device driver. So basically, the reason ACPI came about is that previous implementations of power management, for example, the Advanced Power Management spec, basically relied on calling into the BIOS, and vendor implementations of this were pretty buggy. So the idea was to kind of abstract slightly so that we have some updatable tables in the BIOS that have these virtual instructions that tell the device driver how to perform certain power management functions. For example, how to retrieve the temperature from the motherboard, or how to move a device into another power state. So how might we go about abusing ACPI? As I said, the BIOS holds these tables containing these virtual instructions. The operating system has a device driver that contains an interpreter for these virtual instructions. And this virtual instruction set allows us to pretty much do anything to the system. So we can come up with virtual instructions that allow us to modify system memory, modify the I/O space. So the attack is simply we take a BIOS, crack it open to its code modules and data modules, locate the ACPI tables, disassemble the ACPI tables from the ACPI machine language, this AML, into ACPI source language, which is the high-level language that platform designers write ACPI functions in. We can then modify these functions, recompile them back into AML, put them back in the BIOS, archive the BIOS back up, compress it back up, reflash it, and then ultimately when the device driver, the ACPI device driver kicks in and starts interpreting these instructions, it will interpret our instructions, which will modify system memory and deploy the rootkit. Benefits of ACPI rootkits, especially over the other two methods I talked about. We can make it independent of the operating system. ACPI is a spec that isn't tied to a particular OS. So AML is platform and OS independent. ACPI has this high-level language, the ACPI source language, and so it's easy to disassemble the ACPI machine language back into this source language, and then we can modify it and recompile it pretty easily. Unlike the previous two attacks I talked about, when the AML is interpreted, the kernel is already loaded. In the previous two attacks, we were coming in the bootloader phase before the kernel is loaded. We don't need to worry about that with AML. We can just patch the kernel directly. Also, because we have this interpreter, we can put some logic in there. We can make smart decisions about deploying our rootkit. Has anything changed in the system state since we last infected? If we're using a rootkit that relies on hard-coded offsets in the kernel, for example, then it would be prudent to add some verification that, say, the kernel hasn't changed. Limitations of ACPI. Again, we must be able to update the system BIOS. The operating system must have an ACPI device driver. So in order to detect these types of rootkit, we can simply prevent the ACPI device driver from loading. The system will probably still boot. And also the operating system, or actually the device driver, mustn't sandbox the AML interpreter at all. So for example, when I demoed this on Windows, what I noticed when I was deploying the rootkit was that I was getting a ton of event log messages, which basically came up saying that what I was doing was probably not very sensible, but the ACPI device driver was going to let me do it anyway. But it kind of warned me. And you could easily see that the device driver could be modified to prevent me actually writing to critical kernel structures. Okay, finally, for legacy BIOS attacks, we'll talk about warm reboot attacks. So all of my previous attacks have involved modifying some piece of firmware, making some persistent modification to firmware. And ultimately, this is going to make detection a lot easier. If we think about production systems, for example, a web server with an SLA that requires it's up 99.995% of the time, it's not going to be cold booted very regularly, maybe just to do some maintenance. But it might be warm rebooted, so every month maybe to install some updates. So on most chipsets, we can actually take advantage of the fact that it's just going to be warm rebooted. And essentially, when you actually cold boot, what happens is the CPU starts executing. It issues a read which goes to the memory controller, which will forward it to the firmware device. And as that data is retrieved, it will actually be cached in RAM. On subsequent reboots, we'll typically bypass a lot of the initialization that happened on the cold boot and simply execute code out of RAM, shadow RAM. So we can actually simply, from the operating system, we can simply remove the write protection on these pages in RAM and modify RAM directly. And then we do a warm reboot and our code executes. I guess, unfortunately, from a rootkit writer's perspective, techniques for doing this on different chipsets, they're all unique, basically. So Intel has PAMs, programmable attribute map registers, AMD has MTRRs, memory type range registers. Okay, moving on to legacy BIOS limitations. So the BIOS is typically written in assembler, and really these days, who writes real mode 16-bit assembler? Not many people. And also the BIOS is firmly rooted in the interrupt model. There's very few cleanly defined interfaces exposed by vendors. An example of this is if we think about interrupts as interfaces exposed, then we only have 256 possibilities. So typically what you'll find is that interrupt handlers then break it down into various sub-functions. And 15 hex is a good example of this. It's the miscellaneous interrupt. And basically the sub-functions totally vary from vendor to vendor. The interfaces that are defined are pretty clunky. So if we take a look at the Post Memory Manager spec, which is designed for a code module to be able to allocate memory using this specification. Basically, it's a huge amount of work for us just to even get to be able to use the PMM. We need to start scanning for particular structure. We need to then perform checksums. It's certainly not an easy approach. Okay, so now I'll actually start talking about EFI. Firstly, I want to talk about some of the EFI design principles. What were Intel thinking when they came up with it? What did they want to improve upon the original BIOS? Firstly, they wanted to make sure they reused existing technologies where possible to speed up the adoption rate. EFI has a system partition, which is simply FAT. Executable images within EFI are PE or PE32. Which is the 64-bit PE file. It also makes use of ACPI and SMBIOS, or rather it keeps them in place. Extensibility and modularity were key design principles. So you have the core EFI implementation, which is stored in firmware. And then you have this idea that the environment can be extended by third-party drivers, and those drivers can exist on disk or in firmware. You can develop drivers or applications for EFI basically in C. And EFI is platform agnostic. EFI is the interface, it's not the implementation. To get around the option ROM issue of simply having x86 code in a ROM, we have the concept of EFI bytecode, which is an interpreted instruction set. So essentially we can create an option ROM that will work on multiple architectures. So a high-level diagram of what an EFI environment looks like. To turn on the system, we have the power on self-test as we would in an original in a legacy BIOS. The firmware then initializes, and then we begin to iteratively load drivers and applications. And ultimately, we have a bootloader. The bootloader finishes using the set of services known as the boot services, which I'll talk about shortly. It basically signals to the EFI environment that it's finished using these boot services. It's loaded the kernel and it's ready to transfer control to the kernel. Go through some key definitions for the EFI environment. Protocol is essentially an interface exposed by a driver. Each protocol has a GUID, so this ties in with the extensibility that, unlike the interrupt 15 hex, where vendors were just ad hoc defining various subfunctions, essentially if they use a GUID now, we're not going to have collisions. And it's worth noting that a driver can implement multiple protocols. We have a key data structure, which is the EFI system table. This is passed to every application and driver and essentially allows them to access services and protocols, for example. We have the concept of boot services, which are the services available in an EFI environment. These are kind of the handy services that every application or driver will need to make use of. So we can rely on the boot services for allocating and freeing memory. We can rely on them for locating protocols for us. We have standard IPC and kind of events, timers, that kind of thing. We also have image services. We can actually find out what modules are loaded. We can actually load other drivers, that kind of thing. We then have the concept of runtime services, and these services are available post-EFI. So ultimately, when the bootloader takes control and it signals to the EFI environment that it's done using the boot services, they are no longer available, but the runtime services remain. And runtime services allow us to interact with variables. If anyone's familiar with open firmware implementation, they'll probably know about the variables stored in NVRAM. I'll talk more about those in EFI later. Runtime services also expose time services and some virtual memory services. Next definition is the framework, which is Intel's reference implementation, and this appears to be what Apple have chosen to use. Interestingly, it's partially open source as Tiano, so I recommend anyone that's interested visiting tianocore.org and downloading it. And I found this in one of the specs that, perhaps unsurprisingly, Intel views the framework as their implementation of choice. Let's talk about EFI and security. EFI 1.10 spec is not essentially focused on security. The framework spec, remember the framework's the implementation, they do elaborate on the security phase. But simply looking at the EFI 1.10 spec, it's not so clear the role that security plays. The security phase, the sec phase, should be the first phase in the framework. So essentially, when you power on your machine, that's the very first phase we enter. It's responsible for handling platform restarts. It's also responsible for creating a temporary memory store. When we've turned the system on, we're likely not able to access RAM at that point because we haven't configured the North bridge. So it's up to the sec phase to actually provide a small memory store, typically by using the processor cache. It also serves as a root of trust in the system. This is important from a security perspective. If you're going to create a root of trust, you have to do it as early as possible, obviously, and so it's typically done in the sec phase. And the sec phase hands off to the PEI, which is the pre-EFI phase. The pre-EFI phase is responsible for loading low-level hardware drivers, essentially. So typically drivers for the chipset. Of course, all phases must maintain the root of trust, and the key objective of the pre-EFI phase is to get you to the point that you can then load the driver execution environment, and then we can start loading the interesting drivers, the drivers that actually talk to devices on the bus. So this is kind of what it looks like with the various phases. This is taken from Intel's framework documentation. We can see that we have the security phase, followed by pre-EFI, driver execution. And we get to the point of loading bootloader, and then we exit the boot services, and so the APIs, the functions available from the DXE phase are no longer available, but the runtime services are. So onto the interesting stuff. How can we abuse EFI? Basically, the first objective is get code into the EFI environment. A few different ways we can do this, and these range from the easy to the more tricky. We can simply modify the bootloader itself. Bootloader file on disk, we can simply patch it. We can, slightly more stealthy, we can modify the NVRAM bootloader variable, as in the variable stored in non-volatile memory that basically says what bootloader should I start, or what boot manager should I start. We can actually target the platform firmware itself and patch the core EFI framework. Or we can go for a code injection attack. And these are going to be important when we have an environment that enforces signed drivers. So essentially, by implementation flaw, I mean we look for something like a buffer overflow to get our code in there. That's our first objective, simply getting code into the environment. Next, we have to actually subvert the operating system somehow. So an easy way to do this is we can shim a boot service or a runtime service so that when the bootloader calls that boot service or runtime service, it executes our code. And the bootloader is responsible for loading the kernel. So if we pick a good boot service to shim, or a good runtime service, then the kernel will already be loaded and we can simply patch it. We can modify the ACPI tables, very similar to the attack against legacy BIOS. We can, although in that instance the ACPI tables will be in physical memory at that point. We can load a driver into system management mode. This is one of the more interesting areas of EFI and rootkits. I'll discuss that in detail shortly. Finally, if the EFI environment is about to load a compatibility support module, as in it's going to actually load a legacy bootloader, for example, Boot Camp loading Windows, then we can carry out attacks more similar to traditional BIOS attacks. So, go through these quickly. Modifying the bootloader binary itself. OS X doesn't actually use EFI system partition. It's on the main HFS Plus partition, and it's simply boot.efi at that path. So we can simply patch that file. Apple's implementation doesn't verify driver signing, doesn't verify signing of EFI applications. This isn't really very stealthy. Ultimately, we're just patching a file on disk. If you have anything like Tripwire, any operating system integrity tools, then they'll flag it unless the rootkit's already thought of this in advance. Really, if we're just modifying a file on disk, why don't we just patch the kernel? And this won't work in environments where we have driver signing. Modifying NVRAM variables. So we have the concept of these global variables that are persisted in non-volatile RAM, and they specify which bootloader we should execute. EFI provides an interface for reading and writing variables. The operating system also provides a tool for doing this. So we can create our own bootloader, and we can simply modify a variable in the NVRAM and say use our bootloader instead of boot.efi. Typically what we want to do in our bootloader is we can either patch the environment somehow. We can either insert a shim and then call the original bootloader. And actually the variable name we'd need to do this is the EFI boot device variable. Is this stealthier than just modifying the original bootloader? Probably not. It does leave the original bootloader intact, but we've now modified NVRAM, and that's pretty obvious if you're carrying out forensics. Again, it won't work if the environment enforces driver signing. Code injection attacks. These will be useful when we do have an environment that enforces driver signing. Ultimately, we're looking for an implementation flaw in the driver, a traditional security flaw like a stack overflow or a heap overflow. One thing I haven't mentioned is that the EFI environment is protected mode with a flat memory model, which with no paging. So exploiting drivers is fairly easy, assuming you have a flaw in the first instance. And you might say, well, where would we look for an overflow? Well, there's plenty of targets, really. Anything that passes data that we can modify as a target. So we have file systems. So we could, that should just be fat, but we could modify the file system structure somehow and attempt to cause some sort of implementation flaw in the driver. We can target the PE parsing code. Any code for verifying the PE files is a great target. So any data in certificates, ASM1 decoding, for example, and any data that's received over the network. How might we shim a boot service? I said this was once we have code executing, this is one of the easy ways to subvert the bootloader. Well, the bootloader must signal to the EFI environment that it's exiting boot services. It's exiting the EFI environment and it's about to transfer control to the kernel. It does this by just calling exit boot services. So it's the perfect place to hook because the kernel is already loaded, so we simply just need to patch the kernel. Creating a driver that does the shim is actually very easy. We can get the function pointer for the exit boot services function from the EFI system table. I looked at shimming runtime services, but I didn't actually find many of them that were called. So I think that may be common in future, that the bootloader relies more on runtime services, but ultimately things like eLilo and Grub for booting Linux on, say, a MacBook, they will simply load the kernel, and then, in fact, I have it on the next slide. They will load the kernel, free whatever resources they need to for the EFI environment. They will terminate boot services and then just start the kernel. So you can imagine in step 3 that if we've hooked exit boot services, so executing our own code, at this point the kernel's loaded, it's trivial for us to patch it. Okay, another attack we can carry out is exploiting system management mode. This, in my opinion, is one of the most interesting features of EFI. So system management mode was first introduced in the 386SL. If I take the bottom point before the top one, actually. Ultimately, I think of it as a get-out-of-jail-free card for platform designers. Ultimately, it allows us to execute code opaque to the operating system. So the operating system is simply not aware of it. So you guys are probably familiar with virtualization attacks and virtualization rootkits. You can think of SMM in a similar way. We're able to execute code that the operating system typically cannot see. It can probably detect that it's lost some time between executing 2 instructions, just like virtualization rootkits can be detected. But here are some common uses for SMM. So ACP, we typically use it for handling ACP and things like power buttons on your notebook. It's good for error logging. If, for example, we need to, there's some memory, problems with your memory, we can simply Those can trigger an SMI, a system management mode interrupt. We can log them. Any kind of workaround essentially gets put in SMM, workaround for hardware. And we can get into SMM a number of ways. We can do that via generating a system management interrupt. So we can do that ourselves from the operating system. We can set it up to be periodically fired, maybe triggered by an external event, for example, plugging in some hardware. And the final, well, actually there are many ways, but one of the interesting ways we can also get in is via an I/O access. So we can basically set up the chipset to trap to SMM when it does a certain I/O access read or write. How can SMM be abused? Well, last year at CanSec there was a talk that used SMM to bypass BSD secure levels. And I recommend this for anyone interested in SMM. The paper hinted at the possibility of SMM-based malware, but didn't explore that idea. So what does SMM give for a rootkit or for a rootkit detector software? There's some interesting points. Hardware breakpoints do not fire in system management mode. So if we have any kind of detection software that's trying to detect us with hardware breakpoints, they don't fire. The operating system cannot access SMM RAM if a lock bit is set in the chipset. So SMM RAM is simply some memory in it's obviously some physical memory. Basically, it's often stored in the memory hole created by the video memory. So your video card basically has some memory, and the memory controller redirects access to that memory range to the card, leaving a hole in physical memory, and that's where system management code is stored. Once we've set that lock bit, typically in the BIOS or in EFI, then the operating system cannot gain access to system management RAM. SMIs cannot be interrupted once we're in system management mode, and NMI, unless we explicitly allow it to, cannot interrupt us. And as I said, we can trap I/O reads and writes and jump into SMM. So this is kind of scary from a malware perspective. And as I said, the analogy really is similar to virtualization, except SMM is probably on most people's processors here, whereas virtualization may not be. So why haven't we seen SMM-based malware? A few reasons, though the predominant one is the bar for entry is pretty high. Basically, if you want to debug SMM code, you'll need a logic analyzer. So it's not really the kind of run-of-the-mill script kiddie trying to produce a bit of malware. Also, there's limited opportunity to use SMM from the operating system if the lock bit's already set. So the presentation I alluded to at the top, Luc Deflois, essentially his attack relied on the lock bit not being set. So he was actually able to access the system management RAM. And also system dependencies make it less attractive. Essentially, we don't know what the platform necessarily will be doing with system management mode and what code it already has in system management RAM. So for us to simply blindly overwrite the SMM handler and get it to execute our own code is probably likely to impact stability. So as I said, SMM has been around since 386. So what does EFI do to make it more interesting? Well, EFI provides clean and pretty easy to use interfaces into SMM. So previously, if we wanted to make some SMM malware, we would need a pretty good knowledge of assembler and the CPU. But EFI gives us these nice protocols that we can write an SMM driver in C in about 15 minutes. We have a base protocol for registering a driver, access protocol for whether we set the lock bit or not, a control protocol for triggering SMIs, and we can set up, via child dispatch protocols, we can set up handlers, for instance, periodic handlers. And it also gives us a set of runtime services to use in system management mode, the SMST. So similar to the boot services, though of course we can't use the boot services because we're in system management mode, it actually allows us to handle memory allocation. We can ask it, give me a chunk of memory in system management RAM. It also provides interfaces that abstract access to the CPU context, memory, and I/O space. So how would we implement a rootkit? We could trap I/O access. We could then modify the CPU context somehow. Or we could set it up so that we have a periodic SMI So our code is periodically monitoring the operating system and changing what it needs to in the kernel. What about security with SMM and EFI? Well, ultimately, it's the responsibility of the SMM phase to continue verifying the chain of trust. If we're not verifying the chain of trust, then we can simply go straight in with an unsigned driver. Actually, I'll show you some code to write an EFI driver. So I'll make this font a bit smaller. So essentially, this is our entry point for our driver. And really, this is all just standard EFI initialization code to locate the SMM protocols that we need. So we locate the base protocol, we locate the periodic protocol. We then actually use the base protocol to check if our driver is already being called in system management mode. If it's not, we're calling it because we want to load it into system management mode. So essentially, we use the image services from the boot services to actually get the path to our driver. And we pass this into the register function of the base protocol, and it loads us into SMM. Commented out code to immediately unregister us. And then, once we've loaded our driver into SMM, we register a periodic interrupt, a periodic SMI. And you can see that, where is it? I'm calling a function periodic dispatch, which is located up here. And this is basically, we'd get called in system management mode periodically, and then we have full control of the system. We can query physical memory, examine the state of the kernel, modify it however we need. Okay, moving on briefly to compatibility support modules. These provide backwards compatibility for legacy bootloaders. Examples, the XP on Mac project that beat Apple to boot camp basically, and demonstrated that it was actually possible to boot XP on a Mac. And I guess more widely known is Boot Camp itself. And these are both forms of compatibility support modules that essentially implement the BIOS interface required for the bootloader. So essentially, they implement the IVT, the vector table, and you'll typically find that the interrupt handlers are thunks to 32-bit protected mode code, EFI code, and then we thunk back and carry on executing our real mode bootloader. Attacking these, then we can simply use the attacks that we had against the legacy BIOS. We can target the IVT in particular, or we could patch the handlers. Talk briefly about UEFI. UEFI spec is based on EFI 1.10. UEFI is a consortium of major hardware and software vendors. So EFI was basically developed by Intel, and then they gave that spec to the consortium, which has all the major players: Apple, Microsoft, Phoenix, Toshiba, for example. UEFI actually starts to provide further information on security. So it gives us some further information on driver signing, actually what you should be signing. And it actually, the Trusted Computing Group have now released specs for UEFI and how to tie that in with a TPM. This is basically taken from the UEFI spec describing how signature verification should happen for signed drivers. And essentially I wanted to put this up because in my experience as a security consultant testing a number of different products that had to do PE passing, so for example Think Antivirus, the number of implementation flaws I found in PE passing is like off the scale. So this is quite interesting that it'll be interesting to test implementations of this. I'm pretty sure that at least one vendor will end up having some sort of bug, implementation bug that lets us hit code execution, or they'll be verifying the wrong thing. Okay, some conclusions here. EFI offers a pretty large attack surface compared to a regular BIOS because it's extensible. High-level development tools essentially make it more of a target. They're lowering the bar to attacking the BIOS, or the pre-boot environment, sorry. The third-party driver model is interesting. In environments that we don't have driver signing, then it's extremely dangerous. I found the EFI spec to be pretty vague on security. There's also this kind of blurred relationship between the spec, the EFI spec, and the framework spec. The framework actually started to provide more information on this is what the sec phase should look like. But of course the framework is Intel's implementation, whereas EFI is simply the spec. I guess it would have been nice to see more concrete information on the security interfaces in the EFI spec. But UEFI does make things clearer, but I suspect there is plenty of potential for code injection attacks against UEFI. So that's the end of my talk. As I said, I'll be releasing a white paper that goes into somewhat more detail. I apologize if people are expecting more EFI content or more explicit OSX content. I was kind of a bit pushed for time in putting this together at the end. But if you will check back to the NGS software website, then hopefully you won't be disappointed with the white paper that's forthcoming. And here are some references if anyone's interested. The Tiano core is, as I said, is really interesting as it's an open source implementation. And system management mode, I highly recommend checking out Luc Duflois' presentation. Thanks.